Okay, good afternoon, everyone, and welcome to our session on how to design your generative AI applications for resilience. And actually, Jennifer and I both feel good because our CEO, Matt Garman, if you saw the keynote today, he was talking about the path to production for generative AI, which is something that I've heard from a lot of customers over the last year or so. It's, how do you take a generative AI application and actually run it reliably at large scale for production workloads, especially considering a lot of these applications are end user or end customer facing. And so today we are going to talk about some resilience best practices that you can consider as you're trying to build your generative AI applications. So I'm Randy DeFau, I'm a senior principal architect at AWS, and I'm here with Jennifer.
Hey everybody, thanks for coming to our session today. We're really happy to have you here. My name is Jennifer Moran, and I am a senior resilience specialist, solutions architect here at AWS. And I've been here for a little over 4 years. And as you can probably guess by my title, my job here is to help customers build resilient workloads. And that includes generative AI. So like Randy said, that's what we're going to be talking to you about today. OK, so what we're going to cover today is we're first going to dive deep into the stark differences between building your proof of concept and production-ready applications. So understanding this is really crucial for setting those realistic expectations and planning effectively. Next, we're going to focus on locking down our business requirements. This is a mandatory step to ensure that we're building not just a functional system, but one that truly meets our users' needs and aligns with our organization's overall business strategy. We're then going to explore what a full-stack Gen AI application really entails, and we're going to unpack the various tiers and layers. And before we jump into the resilience properties, we're going to discuss the prerequisite of observability. Because after all, if you can't measure something, then how can you actually improve it? With that foundation, we'll review the resilience properties that any resilient workload should possess. And then we're going to also explore the categories that can challenge these properties. We're going to deep dive into each of these, and we're going to consider both conventional resilience patterns along with some additional considerations that are specific for Gen AI workloads. So by the end of this session, you'll have a comprehensive understanding of what it takes to build truly resilient Gen AI applications. So welcome to the world of generative AI development. It's really a utopian world where there's unicorns and there's rainbows, and it's really beautiful, isn't it? And we're creating proof of concepts have never been more exciting, right? Today, anyone with an idea can bring it to life in record time, thanks to the power of AI. With just a few lines of code or even no-code solutions, you can prototype AI applications and address real-world challenges. So imagine quickly building a customer service bot that handles inquiries in multiple languages. Or maybe a medical imaging tool that assists in early disease detection. In education, you could prototype an AI tutor that adapts to each student's individual learning style. And these revolutionary ideas, once requiring months of development, can now be conceptualized and tested in a matter of days. The ease to create is magical. It opens up a world of possibilities for innovators, entrepreneurs, and problem solvers across all industries and fields. We're standing on the forefront of a technological revolution where rapid prototyping meets AI capabilities, allowing us to turn our most ambitious ideas into tangible proof of concepts faster than ever before. While the ease of creating AI proof of concepts is truly exciting, it's important to recognize that this is just the first step in our journey. The leap from a promising prototype to a robust production-ready application can land us into a world that looks more like this, right? And suddenly, it doesn't look so magical anymore, does it? Well, welcome to the crucible of AI development, transitioning from proof of concept to production. Remember that customer service bot that you built to handle inquiries in multiple languages? Well, now in production, it needs to face millions of queries daily, many in dialects or with context it wasn't trained on. Scaling to meet this demand while maintaining accuracy is a significant hurdle. That medical imaging tool for early disease detection It now needs to process vast amounts of sensitive patient data, raising critical questions about data privacy, security, and regulatory compliance. Not to mention the need for near perfect or perfect accuracy when lives are at stake. And that adaptive AI tutor, it's struggling with the sheer variety of learning styles and educational content, consuming computational resources at an alarming rate as it tries to personalize lessons for thousands of students simultaneously. These challenges, scalability, data privacy, accuracy, resource management, are where our resilience is truly being tested. It's complex and it's sometimes daunting, but it's also where we have the opportunity to build production-ready AI systems that can deliver on the promise of those proof of concepts. And interestingly enough, the first step in this journey from proof of concept to production isn't actually technical at all. It's about locking down your business requirements. So when it comes to building resilient systems, we're often constrained by three big challenges: time, money, and resources. That's why it's crucial to use what we have wisely. And this is where aligning with business impact becomes really important. And even though this is a technical session, I always bring this slide, because when designing for resilience, you need to understand the business requirements. Because after all, resilience strategies must be directly tied to the real-world impact of potential disruptions. So we start with a business impact analysis. This is our critical first step, where we need to quantify the potential impact of failures, including financial losses. So think lost revenue, wasted investments, legal or compliance penalties. Then you have your reputational damage. So this can be loss of trust, negative publicity. After we do our business impact analysis, now we create our risk assessment. Here's where we need to evaluate the likelihood and the severity of the different risks. Things like model degradation, data loss, infrastructure failures, API unavailability. This helps us be able to prioritize our resilience efforts, focusing on the areas that pose the greatest threats. But resilience isn't a simple binary. It involves careful trade-offs. We need to be able to balance the cost and complexity of resilience measures against the potential impact of disruptions and our overall risk tolerance. We can't build resilience in a vacuum. It needs to be rooted in real-world needs and priorities of our organizations. Only then can we develop holistic, risk-informed approach that truly protects the integrity and continuity of our Gen AI workloads. So let's take a look at what a generative AI stack looks like. Randy?
Thanks, Jennifer. So first of all, I'm going to say that I actually don't really like unicorns. They seem like weird flying horses with pointy things on their forehead. Kind of creeps me out. But Jennifer's right about the POC to production leap has been oddly challenging, I think, for a lot of companies. We've seen over the last year, dozens of customers who have a lot of ideas they put through a proof of concept, sometimes investing quite a bit of time and money, and they never actually launch it into production. And there's many reasons for that, including the business case not being clear, the cost being more than expected, but some of it is just really, they're not really comfortable that they can run it at large scale in production reliably and securely. And so the first thing I'd like to do is just look at what actually goes into a complete generative AI solution. I think this picture is becoming more well understood, but about a year ago, this was really less clear. Now, the basis for this diagram, and don't worry too much about the details here, but the basis for this diagram is actually a really good article that Andreessen Horowitz published about a year and a half ago called The Emerging LLM Application Stack. And what they really did is, for the first time, concretely call out all the different things that are kind of coming into play here. Because we start tossing around terms like RAG and agents, and sometimes we really need to unpack, well, what are the things that actually are going into the mix here? And so each of these boxes you see represents a different functional area. And the model is certainly important, but that's just one of those boxes. Even inside that box, there's many choices. You can consume models through a fully managed service like Amazon Bedrock, where it's just an API you call, and so you start thinking about, well, what are the throttling limits and things like that, and what are the SLAs that service is going to offer me. You could also have self-hosted through a service like SageMaker, or through a more DIY approach on Kubernetes or just on EC2. And so each of those has different resilience aspects you need to take into account. But again, that's only one of the boxes. So you'll also notice that we have boxes there for some of our observability components. We have boxes there for some of the trust and safety things, like we need to have guardrails that help detect against toxic input and output. And each one of those, again, has a multitude of ways you can implement it. Some of them an API call through a SaaS provider, some of them relying on open source software, some of them more of a DIY approach. And then at the top, you'll notice we also have, for question answering systems where we're using retrieval augmented generation, we have a data ingest pipeline and a vector database. Now, you probably have data engineers in your company that know how to build a data ingest pipeline, but do they know how to build a data ingest pipeline that has GPUs as one of the performance bottlenecks and is indexing semi-structured data like PDFs rather than pulling streaming data off of Kafka? So if you really look at this in detail, it's not that there's a lot of brand new things here other than the large language model itself, but we're putting together a lot of different pieces in kind of new patterns and potentially with different types of inputs and outputs. And that leads me to another related point, which is observability. I think this is one of the, if you kind of look at the core competencies that I think you really need to be successful with running a lot of generative AI things in production, there's two that have really stood out based on talking to dozens of customers over the past year. One is model evaluation, which is a whole subject unto itself, but the other is observability, because again, these are kind of new combinations of components that have different performance characteristics and different things we need to keep an eye on. And so observability, we now have published like a mental model for how to do this, and we have a reference implementation published on GitHub that has some opinionated tool choices. But there's three things we need to capture. We need to capture, of course, metrics, which is things like how heavily loaded are the GPUs if we're hosting a model ourselves, how many requests are we serving from our inference endpoint, things like that. We have the logs, which help us understand troubleshooting, behavior, things like that. And then one of the things I think is most important with generative AI is the traces. So these have been important for a long time, but they're really important with generative AI because, again, the complete application often involves a kind of a complex series of interactions between the model and the things around it. So if you have an agentic system, you have multiple calls to a model. It's invoking tools. It's querying the vector database to get context back. And if you really want to get a good sense of the state of the system, you have to trace the flow of data and the latency and the errors in that entire chain. And so the mental model we came up with, actually I won't take credit for it, is one of my colleagues, and I just helped them kind of flesh it out. The first layer is the basic component level metrics. So this is things, again, like how busy is our vector database, how heavily loaded are the CPUs on the application servers, how many invocations are we making to a specific model in Bedrock. The second layer are the traces. So again, those are really important for understanding the overall flow of data in the system. The third is the end user feedback. So again, model evaluation is a really important thing you need to become good at because it's not trivial with generative AI. It's not always easy to assess how well a model is performing. So there are ways to do this automatically. There's canned benchmarks. You may have seen that Bedrock announced the ability to use another language model as a judge. But human feedback is still the gold standard, particularly in production. You want to get a sense of how well the model or the application is actually serving your end users. And so having a way to collect this, and not just collect it and observe it as a KPI, but then also use it to drive model behavior to improve it in the future is really important. That's another advanced topic. You can look at post-training alignment, which is basically uses human feedback to kind of teach the model how to perform in a way that humans prefer. And then the fourth layer is really looking at more advanced metrics that kind of dig a layer deeper and look at things like, well, in a question answering system, how well is the model making use of context? Is it factually relevant? You can grade it on all kinds of different criteria like conciseness, factuality, things like that. You can also look at some underlying data quality things like embedding drift. Is the semantic meaning of the questions people are asking changing over time? So these are all important observability things. So with that introduction, I'll give it back to Jennifer to talk about resilience properties.
Thank you. All right. So as we architect for our generative AI systems for resilience, there's going to be 5 key properties that we want to bake into our design. And these are going to be fault isolation, sufficient capacity, timely output, correct output, and redundancy. And each of these properties plays a crucial role, but their true power emerges when they work in concert. So they're not actually isolated concepts, but rather interconnected pillars that reinforce each other. And they create that resilient foundation for not only our Gen AI workloads, but really all of our workloads. And each resilience property faces a unique challenge that can compromise its effectiveness. So let's take and examine these key relationships. So fault isolation confronts a shared fate scenario. And this is where impairments and shared dependencies can trigger cascading failures. This is where those failures are going to cross those intended fault isolation boundaries. We have sufficient capacity is going to expose scalability weaknesses when excessive load is going to push systems beyond their design limits. Timely output is going to struggle against excessive latency as the demand for speed collides with the complexity of AI computations. Correct output is going to contend with misconfiguration and bugs, where the line between error and innovation in AI can become blurred. And then redundancy encounters single points of failure. And these are further complicated by cost constraints and consistency demands. So understanding these relationships allows us to anticipate vulnerabilities and design more resilient architectures. As we move forward, these mappings are going to serve as the foundation for our discussion. We're going to dive into each of these specific challenges that each presents in a Gen AI workload. And we're going to explore strategies to reinforce our resilience properties against these specific threats. So let's start with fault isolation, which is a critical strategy for containing failures within system components, particularly in complex Gen AI architectures. This can be effectively implemented through various architectural and infrastructure level approaches. But first, let's take a look at some of the components that are commonly shared in a Gen AI workload. Randy?
Thanks, Jennifer. So when we look at the things that are shared potentially between multiple generative AI applications or even just individual components that tend to have a large blast radius when we look at failure modes, the first thing I'll call attention to is the vector database. So the vector database is actually a category of different tools that can basically do 2 things for us. They can store embeddings vectors, which are just lists of floating point numbers, and they can retrieve them by doing a similarity search. What's much more important with vector databases is picking them based on the non-functional requirements. So what type of performance do you need? How much data do you need to ingest in a certain period of time? And what type of reliability characteristics would you like? So in the AWS world, for example, you can pick OpenSearch, Aurora, MemoryDB. There's a lot of different choices here. And one thing to call out with vector databases, again, is that sometimes we think, like we do with any database workload, boy, we have a big database, we know how to run it, let's just keep stuffing more things into it. And then you run into a problem where if you're sharing this between multiple workloads, if one workload puts a lot of stress on the vector database and causes it to slow down or become unavailable, it affects all the other applications that are using it. Prompt libraries are another interesting one. So increasingly prompts, which are the instructions you send to the model, are an important resource because they're actually the first and often the most effective way to kind of tailor a model and make it more effective for a specific thing you're trying to do with it. And a lot of times you come up with very carefully crafted prompts, and these can be several paragraphs in length in some use cases. And so you may want to save those as a library or a set of templates that you share between teams. And so changes to this, like changes with any piece of software, can ripple out to all the consumers. If you're fine-tuning a model, so you're adapting it with your own data so it performs better at a specific task, and you're using that model to drive multiple applications, that's another shared resource. And the data you're using to fine tune it is often also shared between different teams. And so now Jennifer's going to talk a little bit about how we mitigate this. And the thing that we'd like to keep in mind is that a lot of the mitigations we talk about are not really specific to generative AI. It's just there's resilience best practices that we're applying here. There are a few things that are kind of unique to generative AI that we'll talk about along the way, but I'll turn it over to Jennifer.
Thank you. Okay, so let's visualize a common scenario where organizations are experimenting with retrieval augmented generation, or RAG. And you can see on the screen, we have some of the shared resources that Randy talked about. And we have a large organization that has multiple departments. So we have human resources and IT working on their RAG proof of concept. Then we have finance, sales, and R&D start developing their own RAG proof of concept. And finally, customer service, legal, and product jump on the bandwagon. And the departments are sharing some of the same resources. So some are using the same vector databases, some are using the same prompt libraries, and others are using the same fine-tuned model. Because it seems efficient at the time, right? Why are we reinventing the wheel? So let's use the vector database as an example of a shared dependency. So the vector database is humming along, it's serving its embedding, it's enabling the similarity searches for all the departments that are using it. Everything's working fine, everything's great. But then something goes wrong with the vector database. Maybe it's a hardware failure, maybe it's a software bug, or even maybe unexpected surge in traffic that's overwhelmed the system. It doesn't really matter what caused the impairment. The point is that now you can see how quickly the impairment of this shared dependency cascades across the organization. So now HR can't access employee records, so leaving staff questions are unanswered. Maybe customer services chatbots are suddenly giving generic responses, and that's frustrating those customers. Legal's contract analysis has ground to a halt, potentially delaying important deals. And product development can't access critical technical documentation, slowing down their work. So what started as a clever shortcut, sharing a single vector database, has now paralyzed critical function across the entire company. So this, ladies and gentlemen, is a textbook example of a shared fate scenario, where we've had an impact from a dependency that crosses intended fault isolation boundaries, in this case, departments. So what do we do? Well, imagine if each department's RAG application used its own vector database and was isolated within a fault isolation boundary. So this can be achieved through various architectural approaches. So we can do a microservices architecture, where each department's RAG application is a separate, independently deployable service. We can use cellular architecture, where we're grouping related services into cells, limiting the blast radius of any single failure. We can do this utilizing different AWS availability zones, ensuring that an impairment in one zone doesn't affect the entire system. We can spread it across multiple AWS regions, providing even greater geographic isolation and resilience. We can even separate workloads into different AWS accounts, such as dev, staging, and production, preventing issues from one environment affecting all the others. And this is a good idea, but let's challenge this thinking for a moment, where fault isolation isn't always the answer and shared fate isn't always a problem, because sometimes things don't fit so easily or neatly into a square box, right? If we could just draw a box around everything, life would be great. We probably wouldn't be sitting here and we'd be discussing how great the unicorn and rainbows are, right? So the key is you have to have a strategic understanding. You need to be able to identify shared fate scenarios, so you need to be able to recognize where your systems are interconnected. You need to be able to understand potential impacts and anticipate how an impairment in one area can affect others. And you need to implement targeted mitigations. You need to choose the right approach for each unique challenge, which may or may not be fault isolation. And now let me stress this point. While we respect each department's unique needs, we strongly advocate for an overarching AI strategy. We don't want to create department silos, but instead what we want is autonomous teams who own their own AI destiny, while still maintaining the overall organizational guardrails and best practices. And the overarching strategy can include things like a centralized data and model governance framework, consistent compliance and adherence across all AI initiatives, unified model training policies to maintain quality and ethical standards. By balancing independence with collaboration, we can create an ecosystem that's not just resilient, but also adaptable and innovative. Okay, so let's turn our attention to sufficient capacity and excessive load. In AI systems, particularly with generative models, scaling isn't just about adding more computing power. It's about smart resource management. So let's start by talking about how load can stress our Gen AI systems. Randy?
Thanks. So the idea that generative AI may be somewhat capacity constrained is probably not new. If anybody here was lucky enough to buy NVIDIA stock 3 years ago, congratulations to you. GPUs are a scarce and expensive resource. And even in the cloud, where we have vast pools of capacity, they're not unlimited. And so it's important to note that large language models themselves may be a very constrained resource. And you'll see this even in Amazon Bedrock. You'll notice that every AWS account has a per region limit for a specific model. So you'll get throttled if you exceed a certain request rate or a certain amount of token input and output. Now those limits can be raised to some level, but you'll notice that there's various things that the Bedrock service has even launched that are pretty unusual for AWS, like cross-region inference, to try to give you some burst capacity into other AWS regions automatically. So in a managed service, these models can be throttled. You'll notice this not only in AWS services like Bedrock. If you go to Anthropic's Claude.ai public website, you'll notice sometimes a day, even if you're paying for the Pro plan, they say, we're under capacity constraints. We're going to revert you to a smaller model, or we're going to revert you to a more concise form. In other words, a smaller amount of output. If you're self-hosting a model, then you're responsible for managing your own system. And so you have to be really careful to make sure that you're not overloading a model. So Jennifer's going to talk a little bit about things like circuit breakers and some other techniques to manage that. One thing that's to note about generative AI that's a little bit different from most applications, even most other ML applications, is that if you're using, say, an inference endpoint on SageMaker or even on Kubernetes, it doesn't auto-scale very quickly. So you can have an auto-scaling policy, but you'll probably want to be pretty aggressive about scaling up. The reason is that these models, particularly the largest models, in order to spin one up, you boot the VM or whatever you're running it on, and then you have to download several gigabytes, sometimes tens of gigabytes of model weights from somewhere, and then load all those model weights up into the GPU memory. So this, the auto-scaling is not anywhere close to instantaneous with these. The vector database is, again, like any database. Let's not forget that this is OpenSearch or Aurora or Pinecone or whatever your database selection is. If it's a SaaS option like Pinecone, it probably has its own throttling limits. If it's OpenSearch or Aurora, you can definitely abuse it. You can, if you're ingesting a huge amount of PDFs all at once, you can kind of overwhelm the writer node, and then you have to watch your read traffic as well. Now, the data ingest pipelines, I think I spent a lot of time in the analytics world, and so data ingest pipelines for Gen AI kind of are interesting to me because most of our traditional analytics ingest pipelines, they're very easily horizontally scalable, right? We're reading text files or we're reading small amounts of streaming data from Kafka. So all of our things like Spark clusters and Apache Flink clusters, they scale horizontally really well because it's really easy to break those things up into small chunks of work and farm it out to a big fleet of worker nodes. With a RAG ingest pipeline, what we're doing is we're taking a bunch of PDF documents or whatever, breaking that up into chunks, but then we're feeding all that stuff through an embedding model, which is a smaller generative AI foundation model that runs in a GPU. And so it doesn't scale horizontally the same way. The GPU becomes the bottleneck there. Things like clustered services like Ray have kind of added features so that they'll adjust their job scheduling and distribution recognizing that the GPU is the throughput bottleneck there. And then finally, again, data ingest pipelines. If you are running a big one and you're uploading millions of PDF documents, you're going to be putting a lot of stress on your vector database. So these are just a few of the kind of unique areas where performance load becomes something to consider in a Gen AI system. Then in moving away from kind of the runtime phase, when we look at fine-tuning and pre-training jobs. So pre-training is when you're building a generative AI model from scratch. That takes weeks on big clusters of GPUs. GPU failures are pretty common when you're doing that. One customer, I think just publicly in their research paper, noted that they typically saw at least a handful of GPU failures a day. Even fine-tuning jobs, which tend to be much shorter, can still be expensive and somewhat time-consuming. So you want to make sure that these jobs, from a performance perspective, can checkpoint their state and you can restart them automatically. All right, over to Jennifer.
Thank you. All right, so what do we do? So traditionally, capacity strategies entailed capacity planning, right, which involves forecasting for future needs and provisioning accordingly. And auto-scaling, again, the number of servers in response to demand. And these are good starting points, but we can do better. So we can augment these traditional strategies with AI ops. So let's see how AI ops can proactively help our capacity strategies. If we use AI-driven capacity planning, we can use machine learning models that can forecast resource needs with precision, allowing for dynamic capacity adjustments that align closely with actual demand. And this can minimize both over-provisioning and performance shortfalls. If we use predictive auto-scaling, we can analyze historical patterns and real-time trends to predictively scale before excessive load becomes an issue. By integrating AI ops into the traditional strategies, we're elevating our capacity management from reactive to proactive, and we're actually using data-driven insights. However, we also know that sometimes more isn't always better. In fact, blindly scaling resources can sometimes lead us down a path of diminishing returns. So let me illustrate this with 3 key scenarios. If we have algorithmic inefficiencies, so a suboptimal designed model or inference pipeline is not going to magically improve with more hardware, right? In fact, scaling such systems might exacerbate inefficiencies, leading to wasted resources and potential performance degradation. If your system is I/O bound, adding more GPU resources is not going to help if you can't feed data to your models fast enough. And coordination overhead. In model training systems, adding more nodes can actually increase communication overhead and data swapping. This potentially slows down overall performance, and not only that, but it's wasteful of your coveted GPUs. However, some workloads, like embedding models, actually thrive on adding nodes because they can run in parallel. So the takeaway here is that the nature of your workload matters tremendously. Scaling isn't just about adding more, it's about scaling smart. So some more scaling smart strategies. So we have model optimization. So techniques like pruning can reduce resource needs without significant performance loss. If we implement intelligent queuing systems that prioritize requests based on business value, user SLAs, or computational complexity, we can go beyond simple round-robin distribution. We can consider the nature of our AI tasks, model specializations, and even the complexity of incoming requests to make smart routing decisions. We can combine edge computing for low latency, high volume requests with more distributed processing across maybe AWS availability zones or regions for those more complicated tasks. We can dynamically choose between different model sizes or architectures based on current load and request characterizations. We can use graceful degradation, where we're temporarily reducing the quality or complexity of generated outputs to handle peak loads. We can do intelligent load shedding, where we're using AI to determine which requests to delay or drop based on system health or business criticality. We can automatically adjust the thresholds for triggering circuit breakers based on real-time system behavior. So remember, the goal isn't just to handle more load, but to do it intelligently. So by implementing these strategies, we're not only scaling the systems, we're actually evolving them. Okay, so in generative AI, timely output is really a delicate balance between speed and quality. And this is only further complicated by highly variable model latency. So unlike traditional systems, the time required for AI models to generate responses can fluctuate significantly based on a number of different factors. Our ultimate goal is to create our systems that balance both this speed and quality, aiming to deliver responses that are not just fast, but also meet the necessary quality thresholds for the given context. So let's start by talking about some of those factors that can impact latency.
All right, so model latency is probably one of the most common complaints that we hear about from customers, where they maybe do a prototype and they're used to seeing a certain P50 or P99 latency, and they move it to production and they find that it's fluctuating wildly. So first of all, it's just important to lay down some groundwork for how we actually measure latency. There's two really common metrics. One is the time to first token, and then the other is the time to get the complete response back. So in a real-time end-user facing system, the time to first token can often be more important because it gives the user the perception that things are starting to happen. There's a few things that affect model latency. One is certainly in a multi-tenant system. It's just if you have a lot of incoming load, then you can start seeing things slow down. Which model you use can clearly drive different latency behavior. So if you look even in the Anthropic Claude family, for example, they have Haiku, Sonnet, and Opus from smallest to largest. All other things being equal, Haiku is going to be much faster than the other two because it's a smaller model. But even for a particular model, it also matters how much input you give it and how much output you're asking for back. So if you look at Claude Haiku, which is generally a small, we think of it as being a small, pretty fast model, if you give it a single paragraph of input and ask it to give you a bullet point summary, that's going to be much faster than giving it a 20-page PDF document and asking it to summarize the whole thing. So that's why measuring latency can be a little bit tricky. There's other things, though, that happen besides just the model. So if we're doing a RAG workflow or we're working with agents, keep in mind that there's things like, well, we're calling out to a vector database and retrieving information back, and that adds some latency. So there's a couple of things that are interesting to keep an eye on for next year that actually I didn't include in that kind of Andreessen Horowitz-based picture. One thing is something called an AI gateway, which is kind of a loosely defined thing right now, but we're seeing a lot more customers get interested in it. This is basically a system that kind of sits in front of whatever the calling user application is and the rest of the Gen AI system. And one of the things it can do is kind of route to different models. And some of that is, as Jennifer mentioned, if you have one model that's overloaded, you can kind of delegate traffic to another model. It may also be that that some requests are simpler, and so you want to send it to Haiku rather than Sonnet, which will give you better performance and lower cost. So there's some DIY implementations based on API Gateway. There's some really good third-party and open source options like Light LLM to look at, but I think those are going to become a lot more popular. The other thing, as Jennifer mentioned, using edge infrastructure is becoming increasingly attractive. The small language models, or SLMs, are becoming really quite good at some of the more routine tasks. And so using those on kind of edge infrastructure, whether that's a mobile device or just something closer to an end user, might also be a good way to kind of decrease latency. Now, I did want to touch a little bit more on agents. So agents are something that a lot of people are experimenting with right now. We're expecting to see a lot more production use cases next year. What we mean by agents is basically a system that has a few different components. So it has a planning or reasoning component that can take a complex task and break it down to a series of actual steps. And then it has some tools it can call if it needs to interact with other systems to actually achieve those steps. And then it has a coordinator that can kind of keep track of which steps have I done and which step comes next. And If we think about a simple example, so I wrote a little application using LangChain, which is a popular open source framework. And I wanted to be able to answer simple questions about what was running in EC2 in my AWS account. And so the model, of course, can't do that on its own. And so I gave it access to a tool, which is just a Lambda function that can issue an API call. And the only tool I gave it was the ability, a Lambda function that could just list running EC2 instances. And so that's the snippet of LangChain code there. And so I said, just list my EC2 running instances. Now, what's really interesting, and this example is a bit old, so it may have improved a little bit since, but it did the first step fine, but then it decided on its own, the model did, that it should not only list the instances, it should get information about each one. And so it tried to call a tool that didn't exist. So this is kind of a funny example, but I've heard about similar things from a lot of customers where they start using an agentic framework from an open source package, and they see very unexpected behavior. Sometimes it just has errors and is problematic, like this simple example. But you'll also notice there's a lot of potential for introducing extra latency here, because the model's thinking, which means it's basically running in a for loop. It's thinking about, how do I approach this? I'm going to call a tool. I'll see what comes back. Then I'll think about the next steps, and on it goes. This is a major driver of unexpected latency for a lot of customers. And so it's important to think about, just as a side note here, full-blown autonomous agents where the model is doing the planning and reasoning step may not be where you want to start. Giving the model access to tools but kind of guiding it may be a much simpler approach. So for example, I could have written a program that just said, okay, model, here's a tool you can call, and this is what it does. And if somebody asks a question like this, you can call this tool. And rather than letting the model kind of reason and start thinking about an unlimited number of next steps. And so in Bedrock, for example, the Converse API supports tool calling, which is an alternative to the full-blown autonomous Bedrock agents framework. Actually, one of my colleagues described it pretty well by saying that if you could think about and draw the ideal flowchart of behavior, you probably don't need a full-blown autonomous agent. Because again, agents can introduce a lot of extra latency and some potential interesting error modes. Okay.
All right. So let's take a look at some strategies that we can use to balance speed and quality. So we can do asynchronous processing with streaming, where we can begin generating and streaming the output immediately, while continuing to refine and improve it in the background. This gives the user immediate feedback, and it actually enhances their perception of responsiveness. And it allows you to gracefully handle those more complex queries that require longer processing time. Again, if we use that hybrid approach where we can combine quick, predictable responses for well-defined scenarios where there are clear rules defined, and then we can allow a handoff to AI for those more complicated queries, or where the rule-based system just can't provide a satisfactory answer. We can use semantic caching. So this is where we can check cache responses to semantically similar questions, which can dramatically reduce response time for similar or related queries, and can ultimately reduce computational load on our models. So we can implement some of these strategies that can balance both speed and quality. And if we just take a walkthrough of a flow where we've implemented persistent semantic caching, and we're using Amazon MemoryDB for Redis in this example. But it's really, the user's going to make a request. It's going to get converted into an embedding. The cache is going to be searched for similar embeddings. And if there's a match, which is considered a cache hit, then the cached output is going to be returned immediately. If there's not a match, which is a cache miss, then we're going to use our knowledge base and our foundation models to generate the output. And then, of course, we're going to store it back in that cache for future use. So as you can see, the fundamental pattern mirrors that of any workload that's leveraging caching, a mechanism. The distinction in the Gen AI workload just lies in the specific components that are utilized rather than the overall architecture. So one of our paramount challenges in Gen AI workloads is ensuring correct output. So we're going to explore how misconfigurations and bugs can threaten this correctness, much like they do in traditional software systems, but with some nuances. In Gen AI environments, correct output isn't just about avoiding crashes or error message. It's about ensuring our models are consistently producing reliable, accurate, and appropriate results. So moreover, the rapid pace of innovation in AI with ever-changing landscapes and tools can further complicate these abilities. So Randy, what are some of the potential sources of these issues?
Thanks, Jennifer. So there's a few things I think that are worth looking at beyond just the usual source of bugs. I will point out that a lot of principal engineers at Amazon have said over and over again that misconfigurations and software bugs and human errors are far more likely to cause problems than infrastructure issues. So this is really worth paying attention to. But one thing I'll call out is the interface between the agents and tools is not often clearly defined. There's a lot of competing open source and commercial frameworks for how you define that contract between the agent and tool it calls, and I think they're still maturing. So you want to pay extra attention to testing these, both for correctness as well as for potential security issues. And again, that's that second point of agents sometimes exceeding what you really would want them to be able to do. So a lot of companies are kind of starting by saying agents can have read-only access to different systems. We're not going to give them full access to APIs and databases and things like that. I'll also call out that a lot of the toolkits we're using for rapid prototyping, like LangChain and Streamlit, these are really good tools. I'm not trying to knock them. But keep in mind that they're evolving very rapidly, and so keep a careful eye on any kind of breaking changes that are introduced when you're upgrading to new versions of them. Also note that this is a very Python-heavy environment right now, so if you're used to an operational world where you have systems like Lang and or Golang and Rust and Java and C# that are more strongly typed and have stronger memory management characteristics, Python needs a little bit of extra attention in those regards. And if you're self-hosting a model, again, keep a lot of attention on GPU performance. It's very easy to get unexpected like CUDA out of memory errors, which throws the system into kind of an unknown, non-deterministic state where the output may not be great. And then finally, just on an organizational level, be aware that you've got a lot of new people in the mix here. So these teams, as you think back to that diagram I showed you of all the different building blocks, you have software folks, data engineers, ML engineers, operations people, prompt engineers. There's a lot of new roles, and so the way they work together may not be perfectly smooth up front. Then on the data ingest pipeline, again, keep in mind that you're doing things like pulling PDF documents out of file systems or maybe pulling CRM information out of an API. And so the error handling and retry logic maybe have to be a little bit more robust than your typical pipeline that's just pulling records out of a Kafka bus. And then with unstructured data, so again, we're talking like PDFs and images and so on, just be aware that the tools that we use in the analytics world for things like cataloging data and access control and permissions, we're not really built with this type of data in mind, and they're still evolving, which means that if you have like a lot of expectations about data consumer, data producer contracts in a data mesh, it may take a little bit of extra work to get there in a reliable way.
Okay. All right. So Randy mentioned some areas where we're more likely to see misconfiguration and bugs in our Gen AI workload. So let's explore some of these and discuss some effective mitigations. So again, we talked about the ambiguous interface between agents and tools. So this can lead to unexpected behaviors. You want to make sure you're implementing that strict interface constructs. You can use tools like protocol buffers, you can use open API specs, but this ensures clear communication boundaries between the agents and the tools. You also want to make sure that you develop a comprehensive integration test that simulates various agent and tool interactions. Because what we want to do is we want to be able to catch these interface mismatches early on. Again, the rapidly evolving tools like LangChain and Streamlit present another challenge. Making sure that you establish a rigorous change management process for tool updates, and also make sure to implement automated testing pipelines that validate new tool versions against your existing AI workloads. The heavy use of Python, while flexible, can lead to type-related bugs. So adopt static type checking tools to catch type-related errors early in the development process. Consider using Python frameworks that encourage type annotations, and again, implement comprehensive unit tests, focusing on those edge cases and type-related scenarios. For self-hosted models like GPU, out of memory, make sure that you're implementing proactive monitoring using Amazon CloudWatch or any other monitoring tool to detect and alert on resource utilization trends. We already talked about implementing predictive auto-scaling solutions that can use these metrics to be able to predict and proactively scale. Consider using techniques like gradient checkpointing to optimize memory usage for these large models. Making sure that you're addressing the challenges posed by these new personas. So develop clear, sorry, I forgot to address there we go. Implement clear role guidelines. You want to make sure responsibilities and best practices for these new roles. And you also want to make sure that they understand how they collaborate and interact with the organization and team dynamics. Make sure that you're using the same mechanisms like peer reviews that you would for any other role that's making changes into a production system. Making sure, again, that you're creating and writing robust error handling and retry mechanisms. So especially in those complex data ingest pipelines, you can use things like AWS step functions if it's complicated to orchestrate, and also make sure that you take advantage of some of the AWS managed services that have the built-in retry and error handling capabilities. And making sure that you have a secure data lake, right? So you have that centralized location for your data, and that you have those governance rules in place that are being abided by. And also adopting chaos engineering. So this is another best practice. So chaos engineering allows us to proactively inject controlled failures into our AI pipelines, revealing how our systems respond to various faults. So you do this via a structured iterative process where you first understand the steady state or the normal behavior of your systems. You then formulate a hypothesis about the system might react when confronted with a specific failure mode. You run the experiment, and the results are verified against the original hypothesis, and then those insights are used to improve the system's resilience. This approach actually allows us to identify and implement missing safeguards to prevent potential failures, enhance your observability to be able to quickly detect issues when they occur, establish your alerting mechanisms for rapid response, and also develop and refine mitigation strategies for those unavoidable failures. You can base your experiments on the categories of failure that we've been discussing as a starting point. And there's a number of different tools and products that you can use to run your chaos experiments. You can use AWS Fault Injection Service, or if you're looking for open source, you can use Chaos Monkey, developed by Netflix. But ultimately, chaos engineering is not about creating chaos, but about unveiling the unknowns in your system. You need to be able to proactively inject controlled failures, and then you can uncover those vulnerabilities. Okay, so our final resilience property focuses on redundancy and eliminating single points of failure in our Gen AI workloads. This critical aspect goes beyond just data backups. It extends to creating redundant components throughout our entire AI pipeline. But for this discussion, we're going to start with the data. Randy?
Thanks. So this should be a fairly easy to understand section. So if we think about what can happen to our data, there's a typical thing. It's data corruption, accidental deletion, malicious activity. So what type of data are we really worried about? Well, if we're running any type of knowledge base or RAG system, we have both the source data and we have the intermediate representation stored in our vector database. If we're fine-tuning, we have the data we use for fine-tuning or pre-training or more advanced scenarios like that. The model artifacts we produce are also important data assets. Other things, the foundation models themselves are important. So keep in mind that if you're using a system like Bedrock, not every foundation model is available in every AWS region. If you're using your own models, you want to make sure that they're available in every region you're operating in. The vector databases themselves, of course, GPUs and model capacity are important. So if you're using like a backup and restore DR strategy, you have to make sure that you have enough GPU capacity in the failover region to be able to stand up your workload. And experiment tracking and monitoring is often a rich source of historical knowledge that we want to be able to protect.
Okay.
5 minutes left.
So let's talk about our data storage strategy. So we want to focus on our critical components that empower our models, right, which is our data. So these elements really are the foundation of our AI capabilities. So reflecting on the 3 primary threats outlined by Randy, data corruption, accidental deletions, and malicious intent, it's crucial to implement a multi-layered data protection approach. So to start with, we want to implement backups within the same region as your primary data. This approach serves as your first line of defense against accidental deletions and data corruption. You can use Amazon S3's versioning, which allows for quick rollbacks to specific points in time, and Amazon OpenSearch enables rapid snapshot restorations. While same region backups are valuable, they don't protect against all types of failures. So to address this, we want to implement cross-region backups as our next layer of protection. This involves storing copies of your data in a different location, potentially another AWS region. However, for even more robust protection and near real-time data availability, or real-time, we can go a step further with cross-region replication. This strategy involves actively replicating data across our regions. Replication is particularly important for organizations with multi-region disaster recovery strategies and where recovery objectives surpass the capabilities of a standard backup restoration process. And then the final layer in our data protection strategy involves replicating data to a separate AWS account. So this provides safeguards against malicious attacks. If your primary account is compromised, you'll have access to a logically air-gapped copy of your data in a secure environment, so you can get back to that last known good state of data. So it's really important to have this multi-layered strategy when we're talking about data backups. But data protection through redundancy is crucial. It also introduces a new challenge known as a redundancy paradox. And the concept illustrates how our efforts to enhance a system's resilience can paradoxically increase complexity. So it becomes particularly complex due to the dynamic nature of data and the intensive resource requirements. So Gen AI models often learn from real-time data streams, such as customer interactions. And maintaining consistency across multiple copies of this ever-changing data is really a significant challenge. So when we try to address this, we're actually introducing complexity to our system design. So we also want to talk about resource management, right? It requires a substantial computational power. Achieving redundancy in compute resources means duplicating those high-performance GPU clusters, right? So this not only increases cost significantly, but also introduces challenges in load balancing and failover mechanisms. So we want to make sure we're using smart resource utilization that we talked about. But really, while redundancy is essential for ensuring the resiliency and reliability, it has to be implemented thoughtfully, right? We need to know, we need to strike that balance between eliminating single points of failure and managing that additional complexity that these paradoxes introduce. Okay, and Randy is going to summarize for us.
So hopefully we just shared some insights with you about what's kind of interesting about generative AI workloads from a resilience perspective. And you'll probably notice I come a lot more from the data analytics ML world. Jennifer's obviously one of our resilience SMEs. I think this is a type of collaboration that can be really useful though. So resilience folks like Jennifer understand how to deal with most of the types of challenges and problems we've illustrated here, although there are a few wrinkles about generative AI that require more data science expertise. So hopefully what your key takeaway was, if we just look at what's really going on with the generative AI workload, we kind of unpack what's in each one of those boxes in the architecture diagram, then we can work with our resilience SMEs to architect a very reliable workload. And this is knowledge that you can, of course, share across all the folks running Gen AI in your organization. So thanks very much for joining us. I don't think we have a huge amount of time left for Q&A, but both Jennifer and I can stay after for a couple minutes, and you can find us on LinkedIn. Our information should be available, I think. And feel free to drop by one of the Cloud Ops kiosks where you can do a VR experience. I think there's some books and some other giveaways. and that's located in the AWS Village. So thanks very much.